Welcome everyone again. So we were talking about semiconductors. Wow. Semiconductors is the workhorse of our industry that makes this beautiful device called MOSFET possible. So now in this video we are going to look at very closely what is this concept of electron and hole. If you have probably heard about, and if you have not, don't worry, we are going to rip it apart to see what is this electron and hole. Why do I even need to talk about hole, right? Why don't I talk about things which are there? So now we were talking about a very important, first of all, our terminology of floors. We said this is our floor 0, which is our valence band. This is our floor 1, which is our conduction band, right? And there are a lot of electrons which are there on this floor 0. All are filled. These are the rooms they are occupying nicely, right? These rooms are called, in the language of semiconductor theory, it is called states, right? Or the quantum states or states which are occupied by these electrons, right? And now these electrons, when we applied a temperature, we saw these electrons, they moved to floor 1, right? That is the promotion. And that happened because you applied a temperature. So when you applied a temperature, you gave energy to these electrons. They say, okay, now you can go like trampoline, go to the first floor. What happens on the ground floor then? What happens on floor 0? When this guy leaves, there is a vacancy or a hole which is created, right? So this has left, and what has created here is a hole, right? And that has come because this electron has moved to the higher floor. So that is what is the empty room now. So then we can define electron as, if we see what is there on the floor 1, that is our electron. So that means occupied room in conduction band or floor 1 is your electron. So you will say, oh, then what is there on the floor 0? These are also electrons. Now I will ask you that if you have a series of thousands of pi, right? And you have to, you know that this is 1000. And you need to know that how many pies are left. Let's say somebody has taken some pies. Would you start counting all the pies which are there? Or would you only count the number of pies which are missing? Right? So let's say what we are saying is n is total number of electrons which are there in the crystal, right? In the whole silicon. We say out of that, let's say one electron has gone there, right? This is what we know as, because this electron is only going to contribute to our conduction, right? So that is what one of the reason why we are counting this electron. We are not focusing on the electron which is n. We are counting on, or n electron, we are counting on only one this electron, which is what we described as small n, right? So that is the n. Small n is the electron density in conduction band, right? That is what it means. So we don't have to count the total number of electrons. We only count how much, what is missing or what has left to the conduction band, right? That is what we are focusing on. Similarly, you could say, okay, I don't need to count all the number of electrons in my valence band because I only need to know how much has been empty, right? So that brings the concept of a hole, which says empty room in valence band, right? So that is your floor 0. So you don't need to count all the rooms which are filled in your valence band to figure out what is missing. You only need to find that which is the empty room. And that is why it precisely, if we are focusing on that what is missing out of valence band, we don't focus on the number of electrons which are left, right? So P is, or sorry, N is the number which has moved. So what is left is this many electrons, but we are not talking about electrons. We will talk about something which is P. Because why do we talk about that? What is left out of electrons, right? We can only talk about how many rooms are empty now. And that is what brings us a very convenient concept, which we say the hole density in valence band, right? That is the basis of what you see electron and hole. So it's a convenience for us to define that rather than focusing on the electrons in the valence bond, we focus on the empty rooms because every room is filled. If every room is filled, where is the information? Information is there, which is empty. Similar to that, we focus on filled rooms in the conduction band because that is information, right? All the rooms are empty, only few are filled. So then let's focus on those. So that is what is called true meaning of information, right? Where you see rather than the data, right? That you are focusing on what is important, what is distinguishing these two bands from each other. So now that means that these electrons are still there in the valence band, right? All of the electrons are there. Some rooms are empty, all are filled. So it's not that the electron, we can still understand the transport in the valence band with the electrons, right? Because electron will also move when the hole goes away, right? But it's better because we focus on the thing which is missing, an empty room, which gives us a very good synergy with the rooms which are filled. So now you see, if we are increasing temperature for each event, there is an electron which is moving and there is a hole which is left behind. So it is likely that we can see for this case our N is equal to P, right? What does it mean? That we are creating number of electrons which are or the electron density is very equal to the hole density which I'm having in my valence band, right? That is the first thing I can say. Now you can ask me, oh, if that is the case, can I keep doing that, right? Or is it limited by any amount? What is happening, right? So let's say I put some people in the first floor, right? And I'm not vacating any ground floor. So it's basically like more and more people are coming in, and I'm not vacating any room from the ground floor, which is what my temperature is doing. But I am just putting those people. What is basically the key metric which is defining the relation between this N and P? And that brings me to a very important concept, which we know as we talked about the Fermi level, right? Last time. You can look at the first video of semiconductor where we were talking about just this floor. Fermi level is the indicator. We talked about Fermi level is your indicator for how many rooms are occupied by electrons on floor 1, right? So they are telling how many of you are, and then you see if this thing moves up, right? That means that your floor, it is like a bar, right? It is moving up. These more and more electrons you are having. But if it is moving down, then you know that more and more holes you are having. So that is the one of the indicator, because it is very likely that if you have more and more electrons occupied, right, you will see that this will move up. And when more and more holes are there, it will move down. But how do we relate this thing is, let's say when this temperature was 0, what was the condition? Let's look at that, right? There was no electron or hole was there. So what was the condition of the crystal? And that is what we know as that all the electrons were only in the bottom, right? So that's what we said, that N and P, they were both nearly zero because there was no temperature for creating them. But as soon as temperature increased, what happens to this N and P, that they were now created by this thing, and that's what we see, that N equal to P, and they were increasing, which is the quantity which we know as something called Ni. Ni is what is our intrinsic concentration. What it means is that you are intrinsic concentration means that you are only using temperature to create or to increase N and P. That is the basic meaning of that. That means the intrinsic means that you are using intrinsic mechanism of the semiconductor. And we saw temperature increase when you are doing temperature. It's a very intrinsic mechanism of increasing this number of holes and electrons. So now one can easily see that how does this even relate to the temperature, because you are saying Ni or N or P are temperature dependent. So then comes the two mathematical equations or two laws, and mathematical equation always comes from the physical phenomena. Physical phenomena which we have seen, for every electron which is created out of temperature change, there is a hole. That is why we say N equal to P equal to Ni. Ni is the quantity which tells you, oh, this is happening because of temperature only, right? So then, there is something called, which is what we know as the mass action, right? Or law of mass action. So how do they two relate to each other is that there is N equal to P, because you can multiply them in intrinsic, that becomes Ni square. Right? That is the law of mass action, which is directly coming from our intrinsic relation. When we just multiply N and P, it becomes Ni square. So that means if there was a condition that I am artificially increasing N, let's say extrinsically, I will use the word extrinsically increasing N will decrease my P, because Ni square is going to be constant. Ni square is just a function of temperature. But if I'm extrinsically increasing, extrinsic means not temperature, right? There's some other phenomena which I'm using, which we'll just talk about in a little while. So then what you see is that you are basically decreasing P if you are extrinsically increasing. If you are increasing with the temperature, obviously that is Ni is also increasing. And how does it increase? So this comes again, how do we calculate this number of electrons which are there with the temperature is related obviously with the fact of this Eg, which tells you how far they are, right, to each other. So you will see that this is going to be the gap between the floors is going to be very important variable, because if you have got energy on the trampoline, how long or how tall will you jump and you will reach the floor? It depends on the next floor height, right? If you jump and then the floor height is less, you are likely to reach, there is a high probability that all of you will reach if 10 people are jumping, right? So that is what is effectively happening on this, that electron is jumping and getting to the first floor, and that first floor is defined, or it's coming separated by this Eg, which is what we called as the band gap, right? So then you see the Ni, which you are going to see is a very strong function of your band gap, which you are going to see. Now you see, oh wow, these new variables, where are you bringing these equations from? It seems like they fall out of the sky. So then you see, no, they are not fall out of the sky, because the very simple way to understand that is, now I have to go to two physical principles. So one was very clearly we talked about, that these rooms, right, which are there. So there are filled rooms here. There are empty rooms which are here, right? That was the story. These are all filled. These are empty rooms, right? So let's say if I'm figuring out that how many electrons have made that jump. So first thing I need to know that how many electrons can be there, right? How many electrons, that means how many rooms are there which are empty, right? And that is what is defined by, oh, how many rooms are there even. That is the question. So that is defined by something called, we know as the NC, which is effective density of states. Right? So that means how many rooms are there is something called that density of states. So now that is one. Oh, okay, this many rooms are available. Now, what is changing the occupation of these rooms is the temperature, right? Which is what we saw. So what was temperature doing? The temperature was changing this probability that these rooms will be filled, right? Because you were jumping on a trampoline and you may land up on the first floor. There's a probability to that. And what defines that probability is the basic workhorse of the semiconductor is known as Fermi function. And if there is an, you want it to be covered in detail, we can look at it in detail, this Fermi function, because this is the key property which defines how the semiconductor behaves with the temperature, right? So obviously this would be a function of strong function of temperature, and that Fermi function is what we defined as exponential of whatever energy you are looking at minus EF by KT. It effectively what you are saying with that. So if this level is your, let's say the level, energy level is EC, this one is EV. So that this is just the energy, potential energy of the floor 1 and floor 0, right? So this is the floor 0 potential energy. This is the floor 1 potential energy. Potential energy, you know, right? All the floors. So now floor 0 to floor 1 potential energy differences, we know it's EG, right? EC minus EF, sorry, EC minus EV, which is the difference between the two potential energy is EG, which we already know the floor gap. Good. So now the question is, how is it filled? So now you see, if we want to know at EC, how many rooms are filled by, tell me. So this relation will nicely tell you how many rooms are filled. So there is an approximation which I could make. There's a mathematical approximation so that it can help you understand better. So let's say if we say EC minus EF is much more than KT, or let's say more than 3 KT to be precise, then this relation, it becomes, because one goes out, because this exponential becomes much larger, so it becomes like this exponential EC minus EF, right? These are simple mathematical simplifications we do for our life to, so Z EC minus EF, it is larger than 3t e power 3, which is much larger than 1. So then you see this becomes equal to EF, so this would be opposite, EF minus EC by KT. Wow. What do you see here? T. My God, T is an important exponential variable. If you are increasing T, you are going to see your probability is also increasing very nicely, right? Because EF minus EC is fixed, right? So you see EF minus EC, let's call some quantity. This one, we call it delta E, for example, right? So then we call this exponential minus delta E divided by KT, right? So now you see, if I increase T, so when T is 0, what is the value? T is 0 Kelvin, right? So e power minus infinity, which is nearly, what is at T0? This is 0. right? FEC is 0, and which is what we saw earlier. We saw that there was no electron which could have escaped from the floor 0, because the probability is 0, and which is what is this relation telling me, that the probability to go to that floor itself is 0 when the temperature is not there. But as soon as you start increasing temperature, you see your FEC, is it going to go up? Yes, because temperature is increasing, bottom is increasing, which is basically, this is like this, right? So if you see temperature is increasing, this is decreasing, then the numerator is increasing, right? That is what. So this probability increases or becomes much, much greater than 0, right? And that is the reason why you see that you start seeing electrons now in your conduction band of floor 0, because this probability. So in the end, you can say that if I were to calculate my electrons which are there in the conduction band, I need to multiply the number of rooms which are there into the probability that these rooms will be occupied, right? This is coming from number of rooms, is what we say as the density of states, and this is coming from your probability of, where it is coming from, it's coming from these rooms, which is what we wrote as EF minus CC by, this is your N, right? So that tells you now that, oh, my number of rooms into the probability is actually telling me how many electrons I'm going to have in my conduction band. Beautiful. That means simple mathematics of number of rooms and the probability is giving me this very, very beautiful relation, which is the key of understanding semiconductor. That is where all the temperature dependence in the semiconductor comes from, is this relation, right? Where the charge dependence on the temperature comes from. And that is why you are going to see this again and again in different devices in different ways, but this KT will appear, right, in some way in the semiconductor devices, because it's at the heart of the how the semiconductor behaves, right? Which is very intrinsic. That's what we said, that it's very intrinsic. Now similarly, I could derive for the holes also. So hole is the number of rooms or number of M2 rooms, right? These are the number of rooms at floor 0, at floor 1, right, into probability that these rooms will be empty, will be empty, right? So then you can basically, which is what known as this NV, which we know as NV, which is the number of rooms we defined at V means subscript means is the valence band, C means is the conduction band, number of rooms. The probability comes now, it is just 1 minus FE, because if FEC was the probability of occupying the electron there, then similar way we could say the occupation. So this, let me talk about. So this is 1 minus FEV, right? FEV is the electron probability, but because we are looking at the, or so FV was the probability of occupation, right? But we are looking at the probability that it is empty. So you know, empty plus occupation is equal to 1. So that means the probability that the room is empty is 1 minus EV, right? And that brings you a relation which we also see as EV minus EF divided by KT, right? This is also, you can work out the mathematics here, the same assumption, and then you will be able to see that this is the relation. So now if you see the two relation we saw, Ni square, one can multiply these two equation, which become NC NV, and if you multiply, this becomes EF minus EC plus EV minus EF divided by KT, right? Okay, and then this EF will cancel. So then it would become NC NV exponential of EV minus EC divided by KT. You already saw that EC minus EV we already defined with a very important quantity, which is what we know in wet gap. So the only thing then left is that Ni square will become equal to Nc Nv, and this is going to be exponential of now minus Eg, which is coming from the definition of the band gap, this Kt, which when I take the root Ni, which becomes root of Nc Nv into exponential of minus Eg by 2. Beautiful, right? This is where this beautiful relation comes with, which is the key of semiconductors. We have seen that if you are increasing temperature, dude, you are going to populate more and more electrons and holes, which is going to increase your conductivity of your semiconductor, which is why you were seeing this current when we saw in the current in the previous video, that this current is coming in the semiconductor when we are increasing temperature, because your electrons and holes are generated, right, with the increase in temperature with this relation. That is the basis of the increase in conductivity of your semiconductor.